Welcome Mechanics of Materials students. This mini lecture goes over a derivation for the shear stress on a cylinder that's subjected to some torque. So this is a clarification of a derivation given in the Vabel textbook. It's example 1.5 of the Introduction to Mechanics of Materials by Vabel, open source textbook. And in the example, the author goes over the derivation for the shear stress on this kind of a ring-shaped area in the middle of a cylinder that's subjected to some torque. So this ring area in the example that is given, having trouble drawing it here, would be a ring-shaped disc, and in this case it's used for an adhesive. So you have maybe a cylinder with a hole in it, maybe made of metal, top and bottom, and then between them there you've put a layer of adhesive that would be shaped about like this, and then that's sandwiched between the two pieces of metal that are basically matching cylinders with that same hole drilled through, top and bottom. And hole is drilled all the way through, and then these tops and bottoms are subjected of the metal pieces are subjected to some torque, and the question is, what is the shear stress on that adhesive layer given a certain radius and wall thickness of the cylinders. And in the example, one of the assumptions that's made is that that thickness is very small. And so if you take a look at the figure that the author sketches, there's a radius established to what is essentially the center or the central mean radius of the cylinders with a hole. So this R, it's a capital R, would basically be equal to 1/2 of, say, the outer radius plus the inner radius. And the author derives a tau based on the applied torque T and this R dimension, and then the thickness of the cylinder. And you can step through that, and you end up getting an expression that just has this R in it, and then there's a note that this requires that T be very small. And in a lot of cases that's true. That is what's known as the thin-walled vessel assumption, and there's some other problems you can go through with normal force that are very simplified by making that assumption. But I wanted to go over what would happen if we couldn't necessarily make that assumption. So I'm going to try to step through here for you kind of how that thin wall assumption gets made in the author's derivation. So this is meant to accompany Vabel example 1.5 in the Introduction to Mechanics of Materials text. So I'm going to start out by getting an expression for, I'm going to match the color here of my little section, of the area of this section here. So I'm going to write it in terms of a radius in my radial direction, some differential angle in my theta direction here, and of course I'm flat, so I don't have to worry about any thickness z. This is just an area, so z is some z, presumably any z. It's going to be uniform in the z direction. So I can express a differential area anywhere that's going to include this slice of adhesive as being r d theta, which is kind of my ds, my circumferential distance, times dr. So there's my typical. So this is d theta, theta, and we're at some average r. So the mean here is my r d theta, and then of course I have a dr here, so that gives me an area. Okay, I can establish a shear force over that area, a dV, shear force, that's equal to the shear stress over that area, assuming shear stress is uniform, and we're going to assume that at this point. Even though there's a lot of edges, we're going to assume that we've taken this area from somewhere down in the middle. It's not up here on a free surface, and so we're going to assume tau is the same everywhere on our slice of interest here. So we can just go tau times dA. Force equals stress times the area over which it's applied, area of application. So in this case we can say dV equals tau, which is uniform, times r d theta dr. Okay, so this is the shear stress anywhere, and I'll kind of redraw our ring here, our little slice. We've got tau, so we've got some shear stress. So it's not hard to see that if we're going to relate this to moment, the radius at which we're applying that shear stress is gonna matter. It's not going to matter, for shear. We're just uniform tau, uniform area, doesn't matter. But if we're worried about relating, or we're concerned, not worried, we're concerned about relating V to total torque, we're going to want to add up the R cross V, starting from that center axis point, for every R and V that we have going. So even if tau were uniform, V is going to be changing with R, and R cross dV equals, we'll call it dm, moment. So R cross F is moment. R cross a little bit of F is a little bit of moment. So this is hearkening back to our distributed load moment that we maybe remember from statics. So we can apply that here to our torque, because we have the right direction for torque. Our moment vector for this torque would be pointing just like that, and if we use our right hand rule, we do R cross V, and so torque's going in exactly the right direction to twist that cylinder, and that was the premise of the problem. So we could express over here a dt equals R, and because everything's perpendicular, this is always perpendicular, I don't have to do the cross product. I can just multiply by R. We kind of have R times F. So we have R times dV, which is all of this. So we end up with R times tau R d theta dr. And we're going to add that if we want to get the torque due to whatever shear stress exists all across this area, all we have to do is add up this torque over this entire area. So all we need to do is integrate over the area of our little thin ring disc. So we can say our total torque is going to equal the integral. We're going to integrate all the way around 2 pi theta. So we're going to go theta from 0 to 2 pi. And then we're going to integrate R from R inner to R outer. And we'll have tau r squared d theta dr. So we can evaluate that, and this is tau, this is torque. So this is the torque total minus the torque, what would be kind of at this first edge, which is 0 basically, because you don't have anything to add up. So it's really the total torque is basically the torque at any point minus the torque at some 0 point where there is no torque. So basically I performed an integral with respect to dt from t at r theta 1 to t at r theta 2. That added everything up. So that just gave me torque total. And that, by the way, is the torque applied. So we actually get, or in the book it's known as T external, is how it's denoted. So if we evaluate those two integrals, we integrate theta 0 to 2 pi, and we integrate r between our inner radius and our outer radius, we can say that the externally applied torque is going to have to be equal to our uniform shear stress times 2 pi over 3 times r outer to the third minus r inner to the third, which honestly doesn't look anything like the tau equals T external divided by 2 pi big R squared times the thickness. But as it turns out, these two really are a lot more similar than you would think. And here's how you go from one to the other. And here's why I put together this little exercise. I'm going to give myself a little bit more room because we have to do some algebra now. So in order to reconcile those two, what we need to think about is the fact that the author did make an important assumption in his calculations to get this expression, and that is the one he pointed out, and that's that T is probably much less than R. So I'll show you where you get that assumption, and this will kind of lead us into thinking way down the road of why, as we get to the end of the course, we'll look at thin-walled cylinders, thin-walled vessels, and then the very last chapter that is in most mechanics of materials studies are thick-walled vessels, and why all of a sudden we need to think of them differently. And this is kind of looking ahead to that and looking at how things look different when this T is or isn't really small compared to R. So if we do a little of algebra and we express R outer, the outer radius here, and R inner in terms of big R, which is the average in T, we can say that R outer is equal to that average R plus T over 2, and R inner is equal to R minus half the wall thickness. So if we look at our outer radius cubed and our inner radius cubed, we would just cube these expressions, which involves a lot of algebra. So R outer cubed ends up being our big R, so that's the mean radius, plus 3/2. And again, this is just algebra, just foiling a binomial expression there. Force big R T squared plus 1/8 T to the third, and then our inner cubed is R to the third minus 3/2 R squared T plus 3/2 R T squared minus 1/8 t to the third. Okay, so in our expression here, we're going to subtract this one from that one. So subtract. So we end up, these terms are going to cancel. Anything that's the same is going to cancel. We're going to get rid of those. So we're going to end up with an expression of 3 r squared t, this should start looking kind of familiar, plus t to the third over 8. I think we end up with 2 of those. Three halves plus 3 halves, so that's 3/4. Hang on, pause, let me factor out my 1/2 and erase. We're resuming minus the skipped step that led to the arithmetic error. We end up having 2 of these, so we end up canceling our 2, and then we end up with 3 r squared t plus t cubed over 4. Okay, so that's what goes in here. So if we substitute that in, remember we had the other terms coming out of our integral. T external equaled tau, the uniform shear stress that was being applied all over that, that adhesive surface. And then we had 2 pi over 3 times this term. Now we have 3 r squared t, get rid of that arrow, plus t cubed over 4. Those 2 cancel, and then we end up with tau times 2 pi times r squared t plus t to the third over 12. Okay, so this first part is our approximate answer that we could see in the VABL example 1.5. This is the new term that we get if we consider t not being really small to begin with. We just basically say whatever it is, we're just going to integrate the stress over it. The only assumption we've made here is that tau, our shear stress that is applied to this face, is uniform all over the face. Other than that, all we did was just like integrate areas and basically integrate our moment over the entire area using our definition of differential moment as the differential force acting at its radius from our axis around which we're taking the moment, which is the center of the cylinder. So only 2 assumptions. If t is really small compared to r, we could basically factor out that t. So let's do that. So we'll just say we have tau times pi over 2. We'll have an r squared plus t squared over 12 times t. If r is really big and t is really small, this is going to basically become negligible in that sum. Even though we've got it multiplied out here, in this sum, if say r is, I don't know, like 1 meter and t is like 1 millimeter, it's going to be lost in the wash even though it gets multiplied out here. So it's a small wall thickness. But in some, like we've got an example in one of the problems where r is something like 20 millimeters and t is 10 millimeters. That's not such a good assumption to make because in that case, those two are really they're within the same order of magnitude. It wouldn't necessarily be appropriate to make that assumption. As it turns out, we don't because in that case, we're looking at a different plane of action on which shear stress is being calculated. But in this case, if you're wondering, if you were working through example 1.5 and wondering how the author arrived at his expression for tau, he did go through this entire area calculation basically, but skipped all of that algebra, and then ended up discarding this term, this t cubed term, just because it was very, very small. Places you may have seen this before. Anytime you've used a Taylor series expansion to simplify a term and like whacked off all but the first one or two terms, that was probably a small angle, a small deflection assumption. And if you remember at the beginning of mechanics of materials, we talked a little bit about how we would be looking usually at small deflections. This isn't a small deflection, it's a small dimension, but it's achieving the same thing in that we can discard a term because it's small relative to the others. Won't always do that. But that's all I wanted to point out here. So if you were working your way through Vabble and you got hung up there, that's the more complete derivation. So if someone says this is a thin-walled cylinder, you can use that much easier and simpler expression relating torque on the cylinder to the shear stress at a cross-sectional plane across it. And in fact, that very configuration with the thin-walled assumption forms the basis of an adhesive shear stress test fixture. It's actually a standard test fixture. Use a little very small thin-walled cylinder that you glue together very precisely so the ends match up, and then you twist it, and you relate measured torque to the time that you begin to see some deflection or failure. And you would use this formula using R and T from your test fixture to calculate your shear stress for that adhesive, and then you can basically determine how strong your adhesive is in shear, which is how many adhesives work. They're usually loaded in shear. So that's it for this problem. So now you can think thick versus thin-walled cylinders and other types of fixtures. You can always drop back to real inner and outer dimensions, but when things are thin, you can make some simplifications.